One of the most important applications for us of direction fields is the logistic equations. We're just going to kind of touch on this here. We're not going to get too in-depth. Of course, you'll get much more in-depth in a differential equations class. Now, why do we need a logistic equation? So keep in mind that the simple exponential growth model that you know and love, it looks like this, it was derived from the fact that the rate of change of a variable y is proportional to the value of y. If we factor in external sources of growth or decay, the model becomes more complicated, but it remains exponential in nature. But the problem is that exponential growth is unlimited, which is not realistic. It's not helpful for the real world because there's always limits to resources, always. And so that means that there's some upper limit past which growth cannot occur. And that upper limit is something we call the carrying capacity, also known as the steady state, which is the maximum population that can be sustained or supported as time increases. So if you look at our next example really quickly, to kind of make this make sense, we'll have the National Parks Commission states the wolf population on Isle Royale, that is an island in Lake Superior in my home state of Michigan. It's the only national park in Michigan. But it's an island, and they had wiped out all of the wolves at some point, humans had. And so they reintroduced wolves into the ecosystem. But there is some carrying capacity. There is some amount of wolves that this giant island can take, and no more. And that's the carrying capacity. It's the amount of wolves that are sustainable on this island. Okay, so that's what a carrying capacity is. It's the steady state. Now, a logistic differential equation model is as such. The growth in the population, keep in mind P is population. I guess I should have written that somewhere. P equals population. Oh, and I'm sorry, I don't know why that got over there. It should say equation right here. Something got weird in my document here. There we go. So logistical differential equation. P is your population. L is, of course, your carrying capacity. It's right here. You see it right there. And K is some constant that's affected by, well, what the island is or what the environment is that you're talking about. What kind of animals are we talking about, etc. So that'll be different for every situation. So P is population, L is carrying capacity, and K is a constant. That's a positive number. So a population that satisfies this equation does not grow without bound. It's going to approach that carrying capacity as T increases. Now keep in mind, if your population is below your carrying capacity, if it's between 0 and the carrying capacity, then it must be true that the population values will grow and increase to the L value as time increases. If P of T is greater than L, so if there's more wolves than the island can sustain, for example, then P of T will decrease, will go down, again, to that L value as time increases. In other words, what we're saying between these two is that the limit as T goes to infinity of my population must be L, which is the carrying capacity. Also known as the steady state. All right, let's look at that example some more with the wolves on the island of Isle Royale. All right, so we have a system here, and if you're paying attention and you're sharp-eyed, you might realize that number right there means that L is going to be 300. This number right here is K, right there, some constant based on your situation. And I have a direction field drawn below. And I want to draw values for 3 different P of 0 scenarios. So P of 0 means at time 0, right, I'm going to have 50 wolves. So I'm going to start off with 50 wolves. And of course I start off with the hardest one to draw. So that's 0, 50. And then I want to follow the lines. Right? The lines won't lead you astray. So you don't want to cross them. You want to go with them and have them be your guide for what your slope should be. But you don't want to cross them over. And then I'm flattening, I'm really flattening. right? You don't want to crisscross over one. You want to let it be your bumpers, right? Your guides, right? It's forcing your curve to follow the contours of that. All right, so that was 50. And then 150, I'll do that one in blue. So I'm going to start here at 150. So it's going to follow the lines. You don't cross the lines. They point the way for your path. There we go. It's going to flatten out. And then that's the blue one. So that was a green one. That was a blue one. And then a purple one. So I'm going to start at 350, which is right here. It's not very high. It's just 50 above carrying capacity. And then I follow the guides, or I try to. It's not easy when you're drawing by hand. And then it's going to go that way. Notice the one that's farthest away from the carrying capacity has the longest way to go up to that carrying capacity, which we can all kind of see is 300. It's right here. Which gets us to the next answer, but we'll get there in a second. But I wanted to verify with you all that what I just did was correct, because I graphed them all already in GeoGebra. So there they are, and that's available to you in the class notes page with the example 5 GeoGebra. So we're looking at this. So there's 150, or excuse me, 050. Looks like my green one. Of course, the computer's doing a much better job than I am, but so be it. And then there's the purple one. And we can see the answer to the last part, that it's got to be 300 is the carrying capacity. So we want to find and interpret that limit. So the limit of P of t is 300. Of course, we're not finding this analytically. We're finding this from the graph, because we don't have the tools in our toolkit to be able to find this analytically in a Calc 2 class. You will find it analytically in differential equations. So it's 300. And I'm kind of giving away the store as to the interpretation part, which is the island has a carrying capacity of 300 wolves. So if the island gets above 300 wolves, they'll die off. There won't be enough food. There won't be enough resources for them. If the island gets below 300, it will climb to 300, which is what this graph shows us.